Imagine drilling a hole into the earth. Not a well, not a mine, but a hole with one purpose: to go as deep as physically possible, to punch through rock that has never seen daylight, through layers of the planet that formed before complex life even existed on its surface. Now imagine doing this for 24 years. This is the story of the Kola Superdeep Borehole, the deepest hole humanity has ever dug. A Soviet-era scientific project so extreme, so persistent, and so strange in its findings that it permanently changed what we thought we knew about the planet beneath our feet. And yet most people have never heard of it. By the end of this video, you will understand what drove scientists to attempt this feat, what they discovered in the process, why they were forced to stop, and why the hole still sits there today, sealed beneath a rusted metal cap on a remote peninsula in northwestern Russia, largely forgotten by the world above it. Chapter 1. The Earth Beneath Us. Before we get to the hole itself, we need to understand the problem it was trying to solve. We live on the surface of a planet that is, in geological terms, almost entirely unknown to us. The deepest mine ever built, the Mponeng gold mine in South Africa, reaches about 4 kilometers below the surface. That sounds impressive until you realize the Earth has a radius of roughly 6,371 kilometers. We have sent probes to the outer edge of our solar system. We have mapped the surface of Mars in extraordinary detail. We have detected gravitational waves from colliding black holes billions of light-years away. And yet the interior of the planet we live on remains in many ways more mysterious to us than the surface of the Moon. What do we actually know about the inside of the Earth? Most of what we understand comes not from direct observation, but from seismology, the study of how earthquake waves travel through the planet. Different materials bend, and slow seismic waves in different ways, and by studying these patterns across thousands of earthquakes, scientists have constructed a general picture of Earth's interior. That picture describes 4 broad layers. The crust, the thin outer shell we live on, ranges from about 5 kilometers thick beneath the oceans to perhaps 70 kilometers thick under mountain ranges. Beneath the crust lies the mantle, a vast region of hot, slowly flowing rock that makes up about 84% of Earth's total volume. Deeper still is the outer core, a layer of liquid iron and nickel. And at the very center sits the inner core, a solid ball of iron roughly the size of the Moon, under pressures so extreme that the metal cannot melt despite temperatures exceeding 5,000 degrees Celsius. This model is our best current understanding. But for most of the 20th century, it was largely theoretical. And in the 1960s, several nations began to ask, what if we actually drilled down and checked? Chapter 2. The Race to the Bottom. The idea of drilling deep into the Earth's crust gained serious scientific momentum in the late 1950s. American scientists proposed a project called Project Borehole, named after the Mohorovičić discontinuity, the boundary between Earth's crust and the mantle, which they hoped to reach and sample. The concept was audacious. The Moho, as it is commonly called, lies only about 5 to 10 kilometers below the ocean floor in some places. In theory, drilling through ocean sediment and thin oceanic crust to reach the mantle was plausible with then-current technology. Between 1961 and 1966, American scientists conducted test drilling in the Pacific Ocean, successfully drilling in deep water for the first time and recovering core samples from beneath the ocean floor. It was a genuine scientific breakthrough, but Project Borehole was plagued by mismanagement, cost overruns, and political controversy. In 1966, the United States Congress cancelled the project's funding, and the effort came to an end before reaching its primary goal. The Soviets were watching. In the context of the Cold War, scientific achievement was as much about national prestige as it was about knowledge. The Americans had reached the moon. The Soviets had launched the first satellite and sent the first human into space. Both nations were locked in a competition that extended into every domain of human endeavor, including, it turned out, the subsurface of the planet. Soviet scientists proposed their own deep drilling program, but with a critical difference. Rather than drilling through thin oceanic crust to reach the mantle quickly, they would drill on land, straight down through the ancient, thick continental crust of the Kola Peninsula in what is now northwestern Russia, close to the border with Finland and Norway. This was a harder, slower, more difficult route. The crust here was far thicker than beneath the oceans. Reaching the mantle was essentially out of the question. But the Soviets were not just interested in the mantle. They wanted to understand the structure of the continental crust itself, a type of rock that had never been directly sampled at great depth. What lay down there? What temperatures would they find? What minerals? What, if anything, would they discover about the geological history of the planet? On the 24th of May, 1970, drilling began. Chapter 3. The Kola Peninsula. The Kola Peninsula is a remote, cold, and largely inhospitable stretch of land in the far northwest of Russia, extending into the Barents Sea. It sits above the Arctic Circle. Winters are long and brutal. The landscape is flat, treeless in many places, and dominated by ancient Precambrian rock, some of the oldest exposed geology on the planet's surface. It was precisely this ancient rock that made the location scientifically interesting. The Kola Peninsula sits atop the Baltic Shield, a region of extremely old crystalline basement rock, much of it over 2.7 billion years old. By drilling here, scientists hoped to read the geological history of the early Earth like a record, layer by layer. A facility was built around the drilling site. It was not a temporary encampment, but a permanent scientific installation. A town, essentially, complete with housing, laboratories, administrative buildings, and all the infrastructure needed to support a long-term research program. The town was called Zapolyani, and the drilling facility itself became known as the Kola Superdeep Borehole Scientific Station. The drill itself was unlike anything used in the oil and gas industry. Conventional drilling systems rotate the entire drill string, all the pipe from the surface to the drill bit, which creates enormous mechanical stress over long distances. The Soviet engineers instead used a turbo drill, a system where only the drill at the bottom rotates, powered by the drilling fluid being pumped down the pipe. This approach reduced mechanical stress and allowed drilling to continue at depths that would have shredded conventional equipment. Progress was measured not in days or weeks, but in years. The drill crept downward through the rock, centimeters at a time, occasionally meters per day on good days, extracting cylinders of core sample as it went. Each core sample was catalogued, analyzed, and stored. The rock coming up from below was essentially a geological library, encoding billions of years of Earth history. By 1979, the borehole had surpassed 9,583 meters, breaking the world record for the deepest borehole ever drilled, previously held by the Bertha Rogers gas well in Oklahoma. Chapter 4. Going deeper. The deeper the drill went, the more the scientists found themselves confronting the unexpected. Before drilling began, Geologists had made confident predictions about what they would find. Based on seismic data and theoretical models, they expected the rock composition to change at around 7 kilometers depth, transitioning from granite-like rock at the top to a denser type called basalt below. This transition had been detected seismically in many parts of the world and was considered well established. It did not happen. The rock stayed granite all the way down. The seismic boundary that geologists had observed and attributed to a change in rock type turned out instead to be caused by a change in the physical state of the same rock. Granite, that had been subjected to such extreme pressure and temperature that its acoustic properties changed, even though its composition had not. It was the same material, behaving differently. The confident prediction was simply wrong. This was the first major lesson of the Kola borehole. Our models of what lies beneath the surface, while useful, are imprecise. The Earth does not read our textbooks. There were more surprises to come. At depths below 3 kilometers, the team began finding water. Not surface water that had seeped down, but water that appeared to have been produced by the rock itself, squeezed out of minerals under extreme pressure in a process called metamorphic dehydration. The water was described by scientists as having an almost primordial quality, unlike anything found near the surface. The presence of water at such depths was scientifically significant. Water acts as a lubricant in geological processes, influencing how rock deforms and how earthquakes propagate. Finding it so deep in rock that had been assumed to be dry and impermeable forced a rethinking of how fluids move through the deep crust. And then there were the microscopic fossils. At depths exceeding 6 kilometers, far below the deepest point at which life had previously been thought possible in rock, the core samples contained what appeared to be fossilized microbial organisms. 24 distinct species of single-celled plankton were identified, preserved in what should have been conditions far too extreme for any biological material to survive intact. The discovery raised profound questions. How deep does life, or the evidence of life, actually penetrate into the Earth's crust? If organisms, or their fossilized remains, exist at 6 kilometers depth in ancient continental rock, what might that imply about the subsurface biosphere? Chapter 5. The Heat Problem. But of all the surprises the Kola borehole delivered, perhaps none was more consequential or more practically damaging to the project itself than the heat. Before drilling began, scientists had estimated the temperature at 12 kilometers depth to be around 100 degrees Celsius. This was based on the average geothermal gradient, the rate at which temperature increases as you go deeper into the Earth, which had been calculated from measurements taken in shallower mines and boreholes around the world. They were dramatically wrong. By the time the drill reached its maximum depth, the temperature at the bottom was approximately 180 degrees Celsius, nearly double the predicted value. The Kola Peninsula, it turned out, has an unusually high geothermal gradient. Heat flows from the interior of the Earth through the ancient rocks of the Baltic Shield far more rapidly than scientists had assumed. For the drilling program, this was not merely a scientific surprise, it was an engineering catastrophe. At 180 degrees Celsius, the rock at depth does not behave like the hard, brittle material you might imagine when you picture granite. It becomes semi-plastic. It flows slowly, under pressure. This means the borehole itself, the carefully maintained hole through which the drill must travel, tends to close. The walls squeeze inward. Equipment becomes trapped. Drill bits are lost in the rock when they cannot be extracted. The deeper the team drilled, the more frequently they encountered these problems. Sections of the borehole had to be abandoned entirely when equipment was lost and could not be recovered. New branches of the hole were drilled around the obstructions, adding complexity and cost to an already demanding project. And above all, the heat made everything slower. Equipment designed to operate at moderate temperatures failed more frequently in the extreme conditions below. The drilling fluid that powered the turbo drill and carried rock cuttings to the surface had to be specially formulated to function at high temperatures. Maintenance became more complex, downtime increased, and progress slowed. Chapter 6. The Final Push. Despite the difficulties, the project pressed on through the 1980s. By 1983, the borehole had reached 12,000 meters, more than 12 kilometers below the surface. Drilling was briefly paused for the team to study the cores already retrieved and recalibrate their approach. When they resumed, they pushed steadily deeper. On the 6th of June, 1992, after 22 years of continuous drilling, the Kola Superdeep Borehole reached its maximum recorded depth of 12,262 meters, or approximately 12.2 kilometers. This is roughly 40,230 feet, or about 7.6 miles below the surface. To put that in perspective, the borehole is deeper than the Mariana Trench. The deepest point in any ocean is beneath sea level. If you could take the Burj Khalifa, the tallest building in the world, and stack 15 of them end to end, they would just barely reach the bottom of the Kola borehole. And yet, even at that extraordinary depth, the drill had barely scratched the surface of the Earth. The distance to the center of the planet from the top of the borehole is approximately 6,359 kilometers. The 12.2 kilometers drilled represents less than 0.2% of that distance. The journey to the core remains, as it was when drilling began, essentially impossibly far away. The Mohorovičić discontinuity, the boundary between crust and mantle that the original Soviet project had never seriously expected to reach, was still estimated to be somewhere between 20 and 35 kilometers below the surface at this location. It might as well have been on another planet. Drilling stopped in 1992, not because the project had achieved all its goals, but because the conditions at the bottom of the hole had become unmanageable. The temperature was too high, the rock too plastic, the equipment failures too frequent. A new target depth of 13,500 meters was set, and drilling resumed, but it was quickly abandoned. In 1995, the project was officially halted. Funding from the post-Soviet Russian government had dried up. The Cold War was over. The era of large-scale prestige science projects was fading. The Kola Superdeep Borehole Scientific Station was eventually shut down, the equipment removed or abandoned in place, and the borehole sealed with a metal cap welded to a concrete pad. Chapter 7. What it all meant. So what did 25 years of drilling actually accomplish? On one level, the answer might seem disappointing. The hole never reached the mantle. It never came close. The distance drilled, while a staggering human achievement, represents a vanishingly small fraction of the Earth's depth. If the Earth were the size of an apple, the Kola borehole would not have penetrated the skin. But measured by what was learned, the project was an extraordinary scientific success. The rock samples recovered from the borehole represent a geological archive of unparalleled depth. Core samples from 12 kilometers below the surface, drawn from rock that is billions of years old, that has never been exposed to surface conditions, that records geological processes from the earliest history of the planet, are irreplaceable scientific material. Geologists and mineralogists have studied them for decades, and they continue to be analyzed today. The discovery that geophysical models based on seismic data can be wrong in significant ways was itself a major scientific contribution. It prompted a fundamental reassessment of how we interpret seismic data and how confident we should be in our models of crustal composition. The finding of deep water in the crystalline basement rock changed how scientists think about the hydrological cycle, the movement of water through Earth systems, and opened up new areas of research into deep crustal fluids. The microfossils found at depth contributed to the emerging understanding of the deep biosphere, the vast, largely unknown community of microbial life that lives in rock, deep groundwater, and sediment far below the surface. We now know that this deep biosphere contains an enormous quantity of living organisms, potentially rivaling the total mass of all life on the surface. The Kola findings were an early data point in that realization, and the heat anomaly, the discovery that the geothermal gradient at Kola was far steeper than predicted, has practical implications for geothermal energy research and for understanding heat flow in ancient continental shields. Perhaps most importantly, the project demonstrated with brutal clarity the limits of what direct observation of the Earth's interior can achieve with current technology. Even after a quarter-century of effort, in the most favorable geological conditions available, humanity could not drill more than 0.2% of the way to the center of the planet. Everything we know about the deep Earth, the liquid outer core, the solid inner core, the convection currents in the mantle that drive plate tectonics, the processes that generate Earth's magnetic field, comes from indirect observation, seismic waves, gravitational measurements, magnetic field analysis, laboratory experiments that simulate deep Earth conditions using extreme pressure and temperature. Direct sampling of the deep Earth is, with current technology, essentially impossible. Chapter 8. The Borehole Today. The Kola Superdeep Borehole site today is a place of quiet decay. The scientific station has been largely dismantled. The buildings that once housed hundreds of researchers and support staff stand empty or have been torn down. The town of Zapolyani, which grew around the facility, still exists, but the drilling complex itself is abandoned. At the center of the site, the borehole itself is sealed by a metal cap, a roughly 20-centimeter disc of steel, bolted and welded to a concrete foundation. It is, by all accounts, an underwhelming monument to one of the most ambitious scientific projects ever undertaken. Visitors who make the long journey to the remote peninsula sometimes report being surprised by how small and unremarkable the cap looks. There is no grand memorial, no museum, no interpretive signage, just a metal plug in the ground, sealing off 12.2 kilometers of darkness. The borehole still holds the record for the deepest artificial point ever created on Earth. Several other deep drilling projects have been attempted since, including efforts in Germany, Japan, and the United States, but none have come close to matching Kola's depth. The German Continental Deep Drilling Program, known by its German acronym KTB, drilled to about 9.1 kilometers in the early 1990s. The United States maintains a program of scientific ocean drilling, recovering sediment and rock cores from beneath the ocean floor, but these do not approach the depths achieved at Kola. There have been proposals over the years to resume drilling at the Kola site or to begin new ultra-deep drilling programs. Advances in materials science and drilling technology have, in theory, improved what might be possible, but the fundamental challenge remains unchanged. The deeper you drill, the hotter and more pressurized the environment becomes, and the more hostile it is to the metal and machinery that need to survive there. The Earth does not yield its depths easily. Chapter 9. Reflections. There is something philosophically humbling about the Kola Superdeep Borehole. We live in an age of extraordinary technological capability. Humans have walked on the moon. Robotic probes have explored the surfaces of Mars, Venus, and Jupiter's moons. We have peered back to the earliest moments of the universe with space telescopes. We have mapped the human genome, split atoms, and connected billions of minds through global networks, and yet the ground beneath your feet, literally the rock beneath the surface where you are standing right now, remains largely unreachable. The planet we call home is, in its depths, as alien to us as any world in the solar system. The Kola project was a reminder that some frontiers are not conquered by intelligence or ambition alone. They require confronting the fundamental physical limits of what matter can endure. Metal melts, rock flows. The deeper you go, the more the planet asserts its own terms. But the project also showed what sustained, unglamorous, decades-long scientific effort can achieve. The researchers who worked at Kola did not make headlines. They did not receive ticker-tape parades. They drilled in the Arctic cold year after year, managing equipment failures and bureaucratic obstacles and shifting political priorities because they wanted to know what was down there. And what they found: the wrong rock, the unexpected water, the impossible fossils, the unbearable heat, changed science in ways that are still being understood today. The hole is sealed now. The drilling is done. But the questions it raised remain wide open. What lies below? What does the deep earth contain that we have not yet found? What would we discover if we could drill further? If we could, somehow, find a way past the heat and the pressure and the slow, patient squeeze of the rock? We don't know. And that, perhaps, is the most important thing the deepest hole ever dug taught us. Thank you for watching Octerra. If you found this video interesting, please consider subscribing. There are many more stories like this one waiting to be told.